The introduction to atomic physics starts with the Bohr model of hydrogen. An electron transitions between discrete energy levels to emit a single, sharp photon. Niels Bohr's early quantization of energy levels provided the first vital stepping stone for atomic physics, explaining how electrons maintain stable orbits without losing energy to the nucleus. While Erwin Schrödinger's wave mechanics mathematically formalized these discrete energy levels, his initial equations still described an idealized, frictionless universe. Empirical reality is far noisier. When we look at real spectrographic plates of heavier elements, the single, clean lines predicted by basic theory shatter into complex clusters of barcodes. This illustrates degeneracy, a state where multiple quantum configurations share the exact same energy level in a simple model, effectively hiding the atom's true internal complexity. Advanced atomic physics is the study of how physical reality, specifically relativity and magnetism, breaks these degeneracies, splitting those single lines into many. This is the total Hamiltonian equation, representing the total energy of a quantum system and guiding our decoding of atomic spectra. The H0 term is the basic Schrödinger equation for hydrogen, calculating the idealized state without interference. To reach physical accuracy, we use perturbation theory. This is a mathematical technique where we layer small corrections onto H0 to account for missing physical interactions. We systematically turn on internal spin, external magnetic fields, and electron repulsion to watch how each term changes the resulting spectrum. Understanding advanced atomic physics requires tracking how this expanding mathematical Hamiltonian maps directly to the physical splitting of spectral lines. From the electron's perspective, as it orbits the nucleus, the positively charged nucleus appears to orbit the electron. This relative motion generates a powerful internal magnetic field. The electron is defined by two vectors, L, its orbital angular momentum, and S, its intrinsic spin. Together, they form the total angular momentum, vector J. Spin-orbit coupling is the physical interaction between the electron's spin magnetic moment and this internal magnetic field. This internal magnetic interaction breaks the energy degeneracy of the H0 state, producing a phenomenon called fine structure. For example, a single p-orbital energy level splits into distinct p1/2 and p3/2 states as the internal field forces the electron into different energy configurations. Transitions between these split states are controlled by selection rules. These quantum gatekeepers dictate that the orbital quantum number L must change by plus or minus 1, while the total angular momentum J can only change by 0 or plus or minus 1. The atom is an internal magnetic dynamo. This internal field is the first hidden variable that shatters the simple hydrogen illusion. We can further probe the atom by introducing a strong external magnetic field, B external, applied in a laboratory setting. In 1896, Peter Zeeman discovered that external magnetic fields force spectral lines to split into even more complex patterns. The total angular momentum vector, J, undergoes Larmor precession, where it spatially quantizes relative to the external B field axis. This process breaks the MJ degeneracies, the states relating to the orientation of the electron's orbit. The normal Zeeman effect is a classical approximation that ignores electron spin, resulting in a symmetrical split into exactly 3 lines. In reality, most atoms exhibit the anomalous Zeeman effect, which proves that the electron spin must be included in the calculation to match laboratory results. The famous sodium D lines serve as the ultimate proof of this anomalous effect, requiring spin-orbit calculations to map their asymmetrical splitting. Applying an external field forces the atom to reveal its complete quantum identity, stripping away the final layers of spatial degeneracy. When we add a second electron, the system's complexity increases due to the massive electrostatic repulsion introduced to the Hamiltonian. Wolfgang Pauli's exclusion principle dictates that no two electrons can share the same set of quantum numbers, requiring multi-electron wavefunctions to be anti-symmetric. Inside a multi-electron atom, there is a constant tug-of-war between electrostatic repulsion and the strength of spin-orbit interactions. In light atoms, we use LS coupling. Here, electrostatic forces dominate, causing individual orbital momenta to combine into a total L, and spins into a total s before they join to form J. In heavy atoms, we use J-jCoupling. The high nuclear charge makes spin-orbit magnetic forces the primary interaction, so each electron's spin and orbital momentum couple into a J value before the electrons interact with each other. These specific coupling states are documented using term symbols, a mathematical shorthand that identifies the multiplicity, total orbital angular momentum, and total angular momentum. To find the ground state, the configuration with the lowest energy, we apply Hund's rules, which prioritize maximum spin multiplicity. These coupling schemes represent physical thresholds where the dominant fundamental forces inside the atom shift as the atomic mass increases. We can shift our focus from valence electrons to the extreme energies of the deep inner K, L, and M shells of heavy atoms. When a K shell void is created by a high-energy collision, an electron from the L shell cascades down to fill the gap. This transition releases a high-energy X-ray photon. Henry Moseley realized that these inner shell X-ray spectra provided a direct way to organize the elements. This chart shows the square root of X-ray frequency against the atomic number, Z. Moseley's law proved that the number of protons, not atomic weight, is the fundamental organizing principle of the periodic table. In a radiationless alternative called the Auger Effect, the energy from the inner shell cascade is used to violently eject a secondary valence electron instead of emitting an X-ray. While optical spectra reveal the atom's chemical behavior, X-ray and Auger spectra bypass that external noise to expose its fundamental nuclear identity. We return now to the full Hamiltonian equation, seeing how each term corresponds to a physical reality. We've seen how internal spin creates fine structure, how external fields cause Zeeman spotting, and how electron repulsion dictates coupling schemes. This journey bridges the gap between the idealized mathematical models of early theory and the messy physical realities found in the laboratory. Atomic spectra are active, structural blueprints of the quantum world. By understanding the rules of perturbation and degeneracy, we can read any spectral barcode as a diagnostic readout of the fundamental forces governing the universe.